So should we start, or I guess, I mean,
I say we should go ahead.
Yeah, I don't want to be very German about it.
I don't know what that means, but we can go ahead and get started if you like.
Okay, let me. So feel free to interrupt me, by the way. I'm okay with that. So you guys can hear me, right? I guess.
Loud and clear.
Cool. So I'm Nuno. I'm from Leiden University. This is not like a sanctioned presentation of any kind, but I'm using the template because I'm lazy. Yeah, and I will speak a bit how AutoML can be used for remote sensing, at least in a very superficial way, which is what I'm doing research on now. Okay, so machine learning, I'm first going to talk a bit about it. I know people have heard of it, sometimes used it, but perhaps don't know so much what it is about. So I'm going to try to explain about that. Then a little bit about AutoML, and then we can try it out with the code that I created. So we can just go through it together and try to make it work in a remote sensing image. So this is the first question. Is this machine learning? I cannot see if you are talking, so you need to speak up. Is this a machine learning example? Take a chance. No?
I don't know.
Yes, no, yes? I don't know. So yeah, so this is not a machine learning example, because basically what's happening here is you have created a bunch of rules beforehand, you have programmed them, and then make it run, and actually the emergent behavior of your agents in this case are very reasonable to real life observations, right? Flocking behavior is a typical example, but it's not a machine learning example because there was no learning. It was coded by the author, right? Which is the opposite, for example, of this example, which is a machine learning example where agents learn to play hide and seek against each other. And what's happening here is you codify some basic rules, and then in order to win the game, the agents need to learn how to behave, and then you can go and explore about this example in the real paper and the 2 minutes paper. But basically here, the models are learning how to protect from each other. And what's happening is these agents are hiding the ramp so that the red agents cannot go inside. So that's how they win the game. They learned how to do that. But in this case, the computer actually learned the behavior. It's totally different from the previous example. So that's the definition. That's the main thing about machine learning. It's actually you substitute the user codifying the rules of some decision. Instead, the computer is going to learn how to do that decision by its own, right? And it's not really a new concept. It has first developed maybe the AI definitions in the 50s, and then it has become more and more, especially with increasing computation, it has become more and more pervasive in everything, right? One of the big discussions recently, you might have heard about it, was that countries and companies which have much more computation power have unequal ability to perform certain tasks, right? So they obviously have a monopolistic behavior in the market. So these are all things that are part of machine learning. The main concept is, in machine learning, you substitute the need to actually do the program. Can you see my mouse? I think so, right? I hope so. But you substitute the need for codifying a certain behavior. Instead, the computer gets the data, gets the output that you want to get, and tries to find a way to make that data result in the result that you want to get. How does it actually work? So I usually give this example. So imagine that you had to do a linear model, and in this linear model, if you forgot linear algebra, and the solution you found to it is I'm going to do trial and error. I'm going to just draw a line and try to draw more lines until I find one line that kind of solves the problem, right? And in this case, you would continue drawing the red one, and then the yellow one, and then the green one, and you will try to reach a line that more or less fits the observation of the data that you have, and you will compare your results from your line against the results of of the actual data, right? And this is precisely machine learning. So what the computer does is trial and errors of different models until it finds one that does not have much error. And the only big difference is that there is some mathematical procedures going to find the best solution. Because if you try it randomly, you'll stay forever trying different solutions, right? So that's the same thing that is happening here. For example, this is, if you remember numerical methods or you study simple mathematics, basically is trying to find the root of this equation. So that's more or less what machine learning is doing when trying to do optimization. That are the three main components, right? At its core, machine learning is about mapping values X into results Y. That's what it does. And then you have something that you call algorithm or representation. So how you create the relationship between the data. You have some metric that you evaluate how good you are performing, and you have some optimization procedure that helps you find the best solution, the best construction of the problem. So that's kind of the whole way computers learn. And in our case of the linear model, the representation is just a linear model. The evaluation is the difference between our equation, our prediction, and the result that you have. And the optimization is actually the stochastic gradient descent. So it's one algorithm to search. So I think this is kind of, maybe I went too fast, but I think it's clear. But if you have any questions about this part, I can take them now.
So Nuno, the optimization part is just about how quickly it learns the solution?
Yeah, no. Yes, of course. And how quickly and how good, right? Because you can fall, for example, in this case, it's a good example. It's not actually selecting the best configuration, right? Because this is a local minima, but the real minima is over here on the left side. So it's about quickness and also about finding the best minimum. Understand the idea?
Yes.
Yeah. So, but there's a lot of optimization is another field of mathematics, of computation, right? There's a lot of optimization research, basically how you can, this is things like genetic algorithms, swarm optimization. There's some dozens of algorithms how to go about this. But basically the three structures of, let's say, machine learning is you have some way to represent relationship between the data, some way to evaluate your model, and then some way to optimize your model. That's the three things that you need to guarantee in order for a model to work.
So the method for optimization would probably vary depending upon the type of data you have or something?
You can vary it optionally. It can be something that you select even. So
oh, okay.
One of the things that you do in machine learning is you can try different optimization algorithms and see which one works better. But in general, people use one or two because they work fine for most cases. And yeah, but it depends. Like, for example, if you wanted to implement something online that people can use, if you have a very computationally intensive optimization algorithm, you might end up, losing all your resources just on that, because you have to compute the results for your client, and then your result too late, let's say. So those kind of things play a role. Any more questions? If not, I'll continue. So when you go about like a random forest, so this is exactly the representation, right? So, and one thing that you always have to notice in machine learning is every algorithm has some kind of minimization happening. There's a concept of something is minimizing or something is being maximized. So this has to do with the optimization part, right? And what happens in the random forest is it maximizes the similarity between clusters of data, and then applies ordinary least squares to those clusters of data, right? So if you have this set of blue, red, and green points on the right, basically it will cluster different groups into these parts, and then fit some model that fits well in that part of the data set. That's how the random forest works. The thing is, every time you want to run a random forest, you have to pre-decide how many trees you are going to use, how many rules are you going to use, how many variables are you going to use on the stitch separation, how many points you are going to, samples you are going to have in each leaf. So all these decisions have to be made beforehand, otherwise you might not get the best version of random forest for your case, right? When you go to support vector machines, it's a similar problem. So in this case, what you try to do is you try to create an hyperplane or a plane that separates clusters of data. And this plane is defined by vectors, and that's why it's called support vector machine. And the idea here is you want to find this special hyperplane that separates everything. And in some cases, your data is not linearly separable, like you see here on the right. It's like a circle thing with the red points in the middle. So you need to do a transformation of the data called the kernel trick in order to find a linear plane in another dimension that separates your data. So it becomes very complicated, but again, the idea is you have to find a bunch of parameters and find which kernel tricks work in your particular data. And these are all decisions that you have to do based not on prior knowledge often, but on specific empirical data that you are receiving at that time, right? So it's not something that one solution fits all. It's every time you have to find whatever is the best combination. And if you go to neural networks that you have heard, so basically neural networks are just super, let's say, linear models on steroids. It's a bunch of linear models working together and interacting with each other. Let's say that's how it works. And the same thing, how many neurons are going to use, what type of layers are you going to use, what type of combinations of neurons are going to use. Are you going to use convolutions? Are you going to use autoencoders? Blah, blah, blah. What type of activation functions? Those are also specific functions in the linear model. So these are all decisions that you to do beforehand in order to find your best model. And what you usually can do is you can try different combinations and see which more or less kind of solve your problem properly. And that happens, that's called hyperparameter tuning. And these parameters like number of neurons, number of trees, tree depth, whatever, those are called hyperparameters. And usually what you can do is you can try multiple. For example, you have a grid where you try different parameters and you see how this changing these parameters is going to affect the result of your model. And you can do it, in a systematic search like a grid, or you can just try random combinations until you find something. More advanced, usually people use now, is something called Bayesian optimization, so which I give a bit more details later. But basically, you try to use a probabilistic approach to try to find which parameters will likely improve your model. So these are all decisions that you have to make in order to ensure that you have a good result. So if you want to automate anything and the client sends you data, for example, and if for every client you have to do this study, then you are always stuck in studying what your client wants, right? So if you want to effectively produce something nice every time, you need to have this automated. Ultimately, what machine learning is and it happens in different applications. This example is from one of my classes. What machine learning basically does is it finds this, this hyperspace that solves a problem, right? And in the case of species distribution models, it's this hyperspace, which is the environmental niche or the ecological niche of the plant, of the target species. And once you have this model, then you can do, spatial predictions about that. Also in remote sensing, we have this kind of three categories of classification. Example today is only in pixel based. It's the more classic remote sensing classification, but obviously this type of logics can be applied for anything as long as you do the necessary adaptations, right? So generally pixel based is based on the spectral response of the objects, and then you try to find different spectral signatures, and your model will learn that. Object based, it's the same plus some morphological information that is automatically detected. Computer vision is totally different, and it's mostly based on morphology of the objects. It can also be integrated with spectral information. Of course, all these things can interact with each other, but these are kind of the three trajectories of classification, and computer vision being the most recent. So do you have any questions about this part, about the hyperparameters? Do you understand the idea?
I guess, when you were talking about the random forest and talking about, you could have a certain set of rules or a number of rules? Does it matter how many rules you have, or does it depend on the data? Or is it just a matter of creating the best rules no matter how many, I guess, parameters there are?
So yes, so so there are parts of the model that try to stop, for example, overfitting. Let's say that you can, in theory, in random forest, you could have enough 1 tree for each sample, right? And then you would have basically a perfect algorithm for those samples, right? Because it will have one decision for each sample. You can generate something like this in theory with decision trees in random forests. It does have some inbuilt methods to stop this from happening, but the thing is, once you are given data, and what really happens when in practical, once you are given data, you try out a bit different configurations, you try out different models, and you end up using whatever works best in accuracy, right?
Right.
If we can automate so that we avoid overfitting and also find the best combination of models or the best model, then that decision is out of your hands and it's a safer decision. The computers will test a lot more than you are able to do in 1 hour, right? In 1 hour, a computer might test some thousands of models, while you might do, 3, 4, 5. Understand kind of what I'm saying?
Yes.
Yeah.
Thank you.
No problem. Any more? Okay, so we go on. So let's say in machine learning, you have this. I just snapped this from the internet. Sorry for whoever wants it. So you have a GIS expert. Those are you guys, right? You get some vector data, some raster data, and you make some nice, maps out of it, or you try to generate new information from that part. So that's GIS expert in our case. And then for the machine learning, you would need some guy that knows about machine learning, and he's going to put it in some model, blah, 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 and then you put it, and you are able to produce a machine that gathers the data, prepares the data, and comes up with a final prediction, and that you can distribute to your client. Often, machine learning, GIS people now are a combination of both, or computer scientists are also a combination of both. So there's not much GIS expert and ML expert. They're kind of very similar now. But these are like the steps you'd have to do. You have to find the data, prepare whatever you need to do with that, choose whatever model is better, train it, evaluate it, find a better model, and then do some prediction that you deliver, right? The problem is that you don't know beforehand what is the best algorithm. You don't know the best configuration of that algorithm. You don't know if you need to do any pre-processing. You don't know if your previous experience with similar data could help. And you will know if you will somehow include this into your process, then you are able to create a service that is actually scalable, right? You don't need one expert for one request from a client, right? And that's precisely the AutoML idea, right? So you get the data, then you go through all this process if you are a normal expert. And in theory, in AutoML workflow, you just skip everything. And all of this is done, it's built into the model. Okay, so it's like trying everything and different combinations with some kind of optimization procedure until you find the best set. Okay, so it's about automating. And obviously, there's a lot of options, of course, like in everything. There's a lot of options, there's a lot of approaches, there's a lot of algorithms you can use, some of them much more, made for computer vision, other ones more for neural networks, other ones more for scikit-learn, which is a machine learning library in Python. So there's a lot of options. But the whole idea is you use these and you are able to get, competitive results. You might not get the best accuracy, but you get competitive accuracy, let's say. That's the minimum, okay? And what happens, it's called in machine learning, this is called the cache problem. So the combined algorithm selection and hyperparameter optimization. So it's exactly what it means. Combining the algorithm selection and also the hyperparameter optimization into the same process, and then be able to produce the best version of the model or the best combination of best models, right? And we'll go through over 2 of them. And one of them was supposed to work, but it's not working anymore. AutoScaler is made here in Germany by the Freiburg Hannover group. It's pretty nice. They keep winning, apparently, a bunch of competitions. And it's basically an AutoML framework built on scikit-learn, which is the machine learning Python library, like most common. And what happens is they design a pipeline of preprocessing of the data, and then algorithm selection, and then it produces an output. It's also a multi-output, which is very nice. It allows you to predict, for example, multiple regressions at the same time. The cache optimization is addressed through two main approaches: Bayesian optimization and meta-learning. So meta-learning is basically they pre-train the model in different types of problems, and they have these pre-trained pipelines. So you start to test the best models by their pipelines, and then once those finishes, it starts finding better ones. So the idea is you spend less time finding the best algorithms because there are some pre-trained pipelines that are similar to your problem. So it's, in a way, it's like if you have an expert, the expert will kind of show, oh yeah, I did something similar before, let's start with this approach first. So that's their meta-learning approach here. So Bayesian optimization, this is a bit harder to explain in terms of mathematics, but what happens is if you have all this, you can see my mouse again, I hope you can see my mouse. If you have this pre-processing, you have a bunch of options of things that you can do in terms of pre-processing, no pre-processing, PCA pre-processing. In terms of the features, if you would like to do something in the data processing, do you need to do the one auto coding? Do you need to find NA values? You need to balance your data set. For example, you have too many samples of one class. And then in terms of the estimator is basically the algorithms, which algorithms you are going to try. So what the algorithm does is going to select, random, if you start randomly, select a random pipeline of preprocessing, rescaling, and classification, and then it's going to use Bayesian inference, basically, which is a probabilistic method to try to find what next solution will provide more improvement, and uses that to try to configure a pipeline. And this is a very nice algorithm, and it really produces nice results, but unfortunately it stopped working. So in my case, that I made for your tutorial, so you will not use it now, but maybe you can adapt my script and just use it for your own test. So basically, it's going to try to find the best combination of algorithms and pre-processing steps. So it does everything for you. You just have to let it run. And the only thing you tell it is the amount of time that it has to do the task. So if we, so then we're going to apply this algorithm. But first, this is the results of the tutorial. So I stole the tutorial from this guy or girl, to be honest, called Sidney Goldstein, and he made an example in R, and he had 4 classes, and he had the data. I just went there and stole from him all the data, and he made a decision tree classification through R, and he got an accuracy of 0.91 and a kappa of 0.89. It's fine. So we have 4 classes spectral classification, right? In the AutoScaler, if it would have run, I only use 7 bands and then I use meta-learning, 60-second string, and 5 minutes cross-validation. And I got a 0.96 accuracy when it was working, and now it's not working anymore. And one of the cool things you could get from AutoScaler is these pipeline explorers, where you can try to find if there are certain algorithms that are working better to give better accuracy, certain pre-processing steps that are improving your model. So you can kind of explore how certain configurations have improved your results. And the final prediction will be given by a combination of the best performing algorithms here. So it's an ensemble prediction. Okay, so this is not working. It's a pity. Hopefully the next version of the AutoScaler, it works fine. So I made another example, which is totally different from Amazon. So this is from the Amazon Web Service people. And they created an AutoML package that allows you to work in images, texts, and tabular data. We are going to use the tabular version. It does not try to optimize the parameters. It's the opposite. Instead, it does this multi-layer stacking approach, which basically is if you have your input data, then you have you run a number of models. Those models then become features for the next layer, and so on. So it's similar to a neural network, but not using neural networks. It uses neural networks, but using more than just neural networks. It's every prediction of the model gets used on the next layer. And this is a very quick approach. So because the main computation problem in hyperparameter tuning is in hyperparameter tuning. So if you don't have to do that, then it's much faster. And that's their approach. And it's actually super effective, to be honest. And does accuracy very similar to the AutoScaler. But the paper was published only this year, so I don't know how they will actually then compete. And if you run my model, then you will see the AutoGluon, reporting a bunch of stuff like what type of task it is and what type of feature preprocessing needs to be done, what type of model is using it now, for how much time is going to use it, blah, 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 blah. So then you can kind of explore if you need to improve the model tuning, all that stuff. So this is the example we'll do after, if you guys want. So basically, automated machine learning. It's about removing the need for a human to be there, or it's a very minimal human presence, let's say, which is very critical if you want to have a service provider online, for example. It can provide a lot more insights than just, for example, classification or regression. If you would like to understand, for example, random forest, you can try to measure variable importance. Neural networks, you can also do similar stuff. Some other models might not give you that information, but because you are using ensemble learners, you can also take a lot more insights from the data, because different models are going to tell you different things. And you can have summary statistics, summary visualization tools like the pipeline profile. And of course, it could be fine-tuned to your tasks, right? These models I'm using now are made for text data, tabular data, other applications. But for example, in the remote sensing, we could implement a vegetation feature generator, for example, that would include vegetation indexes in your model and see if that increases your accuracy, right? Those alternatives exist for our specific field. On the other hand, AutoML is also becoming, it's on the peak, right? So everybody is going AutoML now, but very soon enough, it might go to the throat of disillusionment, and then maybe gets better after that. Okay, so that's my presentation. I hope I didn't take too much. I took 40 minutes. It's okay. If you have questions, you can either write or you can tell me.
Hi, can you hear me?
Sorry.
Oh,
yes,
no, please go ahead.
I just wanted to say thank you. I don't have any questions, but it was really informative. Thank you.
Okay.
Well, I
Problem,
do have a question. Can these machine learning algorithms deal with spatial autocorrelation?
No, but think about it. You can now in terms of thinking of automated. None of this is prepared in any way to do with spatial autocorrelation. But spatial autocorrelation can be an optimization problem as well, right? You can, for example, put an optimizer into your data that is going to undersample your data based on a selection criteria that minimizes the spatial autocorrelation. So those are things, I never tested that, but those are things that can be, inbuilt into the model somehow if you change this type of approach to more remote sensing and spatial analysis, right? Yeah, but I don't think any of this is made for that, unfortunately.
All right, thanks.
No problem. Maximize it. So, no more questions?
No, hello.
Hi.
Yeah, I just wanted to say it was nice. Sorry, I saw your message on your post on Facebook late, but yeah, I came. It was nice.
No problem.
Would you be sharing the PPT by any chance?
Yeah, I can put it here. I can put it here in the Discord, but I think they also record. I don't know if they recorded, but I think they also record.
Okay.
Sometimes the presentations, and if they didn't, it's fine. I will share it.
Okay.
I'm recording.
Great, man.
And
Okay. So who wants to try the algorithm with me?
is that the one that
Yesterday, yes.
Yesterday? Oh. I was the one that failed for me a couple days ago.
Oh. Well, it makes sense.
I could say Colab seems to work the best.
Yeah. So yeah, and this I'll just show you how you can run it in a very simple example. The one I set the accuracy now because it was just to tell what you're going to do. But I could either go onto the real things that go behind these algorithms and then get everybody lost, or go into the machine learning and get everybody lost. So I chose the second one. Okay, so if you don't have questions and you want to do live testing with me, then I'll start the live testing. And you stay here, or you just turn it on your computer. So I gave the link in the Google. I will put it again. So you have to go to my GitHub, and then repositories, and you have these examples, and you go AutoML and AutoGluon, because AutoScaler is not working, and you will have this that you can just open it. My suggestion is you open it in Colab, because then I'm sure your packages work.
Can you
Okay?
can you just link it in the no mic voice chat?
Yeah, I put it on the no voice chat already.
Oh, okay.
As you were asking. So yeah, so then you click this button, and it should.
I gotta take off, but I just want to say thank you.
No problem. Bye. And then you'll have this nice, beautiful code. The worst organized. You have to run your runtime in GPU. It does need, this case does need GPU processing. So that means you need to be quick. Google will kick you out. So you connect to the thing, and then you can start the exercise. So this is not very entertaining, I know. By the way, is anybody trying it, or because if you are trying, you can also share your screen, for example, and we can see if you have errors and stuff like that.
I tried it yesterday.
Cool. I don't know. Very few questions. Maybe I spoke too fast.
No, you did fine.
Thank you.
Yeah.
You guys are all very.
Yeah.
You guys are all very positive. You are very positive in your feedback.
Oh, come on, you are doing all this. I think we should be positive. It's fine. Happy
Yes,
watching.
Thank
Yeah,
you,
I'm just trying to absorb it all.
Pericardial is also, for example, pericardial, I forgot the second name, pericardial epididymitis is also sharing his screen.
I'm running the code again.
Okay. So it takes a bit of time to download all this crap, of course. Part of the life. And it's a pity that AutoScaler doesn't work, because that pipeline profile is really cool to explore how the models work. Maybe I have some old run here. This is actual scientific research now. You have to close your eyes. I think we can just run.
Nuno, would you mind just explaining what Google Colab is? Because before you had me try, this in Colab, I had actually never heard.
Oh, really?
Google Colab.
Okay, sorry.
Really?
Collab is one of the coolest thing you will come across. Sorry.
Yeah.
Go ahead.
Yes, exactly. So Collab is a service provided by Google to help people, have some access to programming and computation parts. It's also provided a paid service, but the free service is already good enough to try models and do learning. So it's kind of a toy research cloud computing system, let's say. That's what I understand from it. So you can use it, for example, to try out computer vision algorithms without having, to install it in your Windows machine, which is sometimes impossible, or to have to deal with your NVIDIA CUDA installation, blah, blah, blah. So you can use the Colab to try out stuff. Of course, it has a lot of limitations. For example, you can only use it for 12 hours, and the computers are not super good, but they are better than mine, so it's fine. So I do a lot of processing here. For example, I use Colab even sometimes to go get data from Google Earth Engine. And that's nice. Of course, it's not super fast sometimes. So let me see if I had a profiler here open, maybe from one of my researches. Sometimes I leave them behind. Oh.
Yeah, so basically it's a collaborative cloud-based platform based on Jupyter notebooks and stuff. Yeah,
much better explained. So that's exactly it.
I was just thinking, it does have a very Jupyter notebook look to it, especially like with the cells and like pressing the run button. It definitely has that impression.
That's exactly, yeah. That's what I don't know who explained, but thank you for that intermission. That's perfect explanation. So, for example, this would be the pipeline explorer that you would get in. This is for another exercise. This would be the pipeline explorer that you would get there. For example, sort by types of actions. So one of the things in the pipeline is to transform the categorical data. The other one is to transform the numerical data, do some class balancing, kernel PCA, these are all preprocessing transformations. And then finally, you have these classifiers. And you can look at this table, for example, and see that the libsvm classifier is performing better than most of the other ones. And then you can even click on it and see like and you can also see which ones are being used in the ensemble. So all this information you could get from AutoScaler is pretty neat, to understand what's going on and to find out which pipelines. So for example, you can do a first run trying everything and then another run trying only the best models. Things are possible in Sklearn. So after you run all these, you have to restart the runtime. You have installed the package that was already loaded. Fine, and then you can run this AutoGluon tutorial. Then you have to get the data from the tutorial. So go and steal the data from Sydney. Sydney was his name, right? I think. These are all nice packages for dealing with raster data in Python, which is kind of horrible. You can try to understand the code, but it's not clean. This was just for you guys. Okay, so then you can kind of see the image that you are going to classify. Is this Landsat image? Of course, you can open this in ArcMap if you want. And you can also see where the points are fitting in the next spot. And this is where the samples are. And I made a small separation, random sample between, training and validation data. I make a directory for the outputs and I run the whole model. This basically is just extracting the values from the bands and putting them into a table somewhere. And if you see the outputs, you'll get the results there. I think I might be going too fast, but this is just clicking and running, right?
No, this is fine.
Then you have import pandas. It's fine. If you have questions, just tell me to stop.
Oh, I was going to say, it's interesting you weren't getting that CRF error.
Yeah, because probably I'll get it if I start to the imports. I think it's some conflict in the package and importations, but ignore it. It has to do with projection, I think. So this basically just generates the two tables. And I was very lazy. I generated like this for AutoScaler, and so I just binned them together again after. Just copy paste it from the other one. Okay, so did I forget to load the AutoScaler? Yes, so like probably it's here. Yep. I think that's the reason why I didn't give an error, by the way.
No, you do. Yeah, from SQL on import model selection.
No, I didn't get this error last time, so it must have imported it and forgot. Okay, so you see, this is a very good coder. So then you run the model and you just tell him what is the data set, what is the target variable, the time that you want to attribute to it. The more time you put, the more models it's going to be able to train. So you can put 600 seconds, and it's going to use all the 600 seconds. But sometimes you can put 1 hour, and it will not use the entire time. It will use only as much as is necessary. And then this has to do with the cross-validation, I think. I left it from behind. I think it's correct. And this hyperparameter slide, if you go to the AutoGluon API, which is not nice, to be honest. It's not a super nice API. They try to make it easy, but it becomes, different. So if you go to the AutoScaler API and you try to see, you have this preset structures, which are explained here what it's doing, and hyperparameter slide. Parameters. Always write this wrong. So you have here light. So basically, it's a small model with some light training of the hyperparameters. You can even make it very light. You can make it very, very strong, whatever. It's up to you. This is kind of optional for you. Okay. You can also, for example, go here and remove some models from the stack, so that for some reason you don't want to use those. You have a lot of options. Then you run the model, and this takes 180 seconds. This task not defined. I forgot to import. Oh yeah, I forgot this. Sorry. I forgot to import task because I skipped that line. If you either run the first exercise, you will not have the same error as me here. Okay, so then you run it, and it's running.
Can I ask a question from the previous chunk of code, the one above this?
Yeah.
Can you scroll a bit? Yeah, a little bit more. So yeah, stop there. In line 7, right where your cursor was, 777. Yeah. What does as type category does? One hot encoding? Sorry, I'm not.
No. So that's a nice question, because usually in a scaler you have to do the one hot encoding by hand. But the AutoScaler and this model, the AutoGluon, actually, if your data is classified as category, they just do the one hot encoding for you.
Oh,
you don't have to do it. So it's much nicer.
Okay, that's great. But your class values are like numbers, right? Class 1, 2, 3, and 4, or it's string type.
Here they are strings. So the AutoGluon is running with them with strings. So the output is a string.
Okay. Okay.
I can show you. It's very cool, right? It's much closer to R. So if I would, go to, for example, let's do the prediction only, right? Oh, yeah. It's just the class now. Develop, water, develop, blah, 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 blah. Understand? So this is nice. This saves a lot of work in in Python. So in R, this is not a problem. For example, in R, usually you work with categories and classes and strings, but in Python, you do have to be, working with numbers and blah, 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 and integers and data types. So if you can avoid that mess, that's great. Only problem is you need to convert it to numbers in order to make an image. So you end up with the same issue in the end anyway. Yeah, this second part is basically just to create the raster. It's a lot of cheating. I have to be careful. I cannot say that word properly. Cheating to do the calculation. So now I'm just going to predict on the array, and this is just so I know what are the classes. And here I transform the classes into numbers. And then I do the rebuilding of the raster, and then I just save it to my computer, my Google Colab environment. And I can download it. I think I was a bit too fast, but it's just clicking the buttons. And where did I put the thing? So I just then drag it over here using my ArcGIS expertise, and I have my classified raster. Right. I probably shouldn't have used 0. I think that was a mistake. That's why I get this weird number. Actually, I can just try it. Let's just do it. Why not? 1, 2, 3. Is it? Sorry, I think maybe I was thinking maybe the reason why my background is specified wrong is maybe because I just gave it a 0 and it shouldn't. I don't know. Oh, that's not the reason. Oh, yeah, that's not the reason. Anyway, that's something I don't know how to correct. I would know if I would investigate. But I don't feel like doing that. That said, you have a nice classified map here with 96 accuracy according to the data that you have. Cool. And it's this would be an automated solution, right? Your client will give you the data and the classes, and you get the results. Did you enjoy? Any questions? By the way, that classification is really bad if you actually go look at the map, but that's not my fault. That's Sydney's fault. He gave me really bad samples. Okay, then it's over. Thank you.
Well, thank you.
Any questions?
Thank you.
Questions? See you around. Iedereen.
Thank you for showing us that.
Yeah, appreciate it.
Bye, guys.
Bye.
Bye.